In this video, my target is that I want to discuss about the mesh requirements for the CFD analysis. So as we know that for any flow, we have the always discussion about the tetra meshing and about the hexa meshing. So let me show you this thing quickly. So you can see that here I have solved the, this is a from the my 4 weeks course, online course that I'm conducting. Next batch is from the May 6, and the course fees is only $65. You can attend that course. So you can see that I have described the problem analytically, like equations, diagram, and also I solved the problem analytically, and then you can see that this is the data, like we have the analytical data that is in the red color, and then we have the three lines, and these lines are actually from the tetra meshing. And we know that the hexa meshing will always produce the very good results. So the reason why the hexa meshing produce the high quality results because of two reasons. Number one is that it has the mesh is aligned to the flow, and we can control the mesh in the boundary layer, and the cell shape is the hexahedron. And number two is that the tetra meshing has a tendency, and this is especially a problem for the internal flows, that it has a tendency that it will grow the size from the surface sizes to the interior of the geometry. So it means that we will be having the very few cells in the interior of domain, and the issue is that this is okay with the external flows. But problem is that when we are working with the internal flows, the mostly the region is is confined with the walls on the all sides. So we can say that all the flow inside the domain is in the boundary layer. So we need the fine mesh. Even the solution overall variables, they are okay. I have compared the mass flow rate, pressure ratio, shear stress, skin friction coefficient, Darcy friction factor. These all values are okay with a very minor percentage difference. But you can see that here, that the graph here in the blue color is from the tetra meshing, baseline mesh. Second mesh and third mesh, they are again the same mesh, but in the one mesh I have put the sphere of influence, and in the second mesh I have put the body of influence. So difference between them is like a very little. From the meshing point of view, sphere of influence is like we create directly in the meshing software, and so it will be refinement region where the mesh will be refined volumetrically. And similarly, for the body of influence, this is like we create in the geometry tools, and then we use that geometry, extra geometry other than our main model, and we use that geometry to refine the region in the local volume region. So difference that the sphere of influence is only of the sphere shape, but the body of influence we can have the any shape. So now let's go to the our case. So this is results, and if I go to the plots, you can see that if I plot the hexa meshing, this is hexa meshing case, one case, and definitely you can see here, if I show you that here, you can see that this is in the pink color. This pink color is a multi-zone mesh, and the number of cells are only 25,000. But while on the other hand, tetra meshing, this blue color contains around 1,60,000 cells, and the other two meshes, they have the lot of elements. So let's go through them one by one. So simple this one. So if I use the tools which are here, the mesh calculator, it's around 4,41,000. So let me go over the these cases over here. So we have the right now we have the 4 cases here. Okay, so one is the multi-zone and 3 are the tetra meshing. So tetra meshing I can show you. The first is the baseline mesh, and you can see here that the volume elements, the boundary layer is okay with the inflation, but problem is that this whole flow is in the boundary layer. As we know that when the flow is fully developed, the boundary layer grows, and this will be matching, will be converging to the middle of domain. So, and also we know that the velocity profile will be like a parabolic. So everything is in the flow is in the boundary layer. So, but you can see that the core region has a very few elements, so that we cannot actually, we can solve the flow accurately, but when we represent data, the data cannot be represented properly. So second thing, which is like a sphere of influence. So only region where I have the line defined, and on that line I'm going to actually plot my velocity profile is refined one. And in a similar way, third mesh is the same element size, but only thing is that we have used the body of influence. So this body of influence is shown here. Okay, and here we have only used the sphere of influence that you can see from here, like this one. Okay, so this is making difference. So one is without anything else. So now this is one contains around 4,41,000 cells, and this is only 1,60,000. This is the baseline mesh, and this mesh contains the how many cells? This contains the 5,16,023 cells. But you can see that even with with the mesh with the sphere of influence, which contains the 4,41,000, second 5 lakh something, and they don't have any difference. So I think that even with a less number of cells, the data will be same. But that's definitely interesting thing is that with the hexa meshing with the very less number of cells, they are only 25,000 around 24,960 cells. The results are more accurate than the tetra meshing. So this was just a point here, and so we have actually solved all the different meshings there and compared them for the pipe flow. And what we did here is that we have gone through the theoretical concepts, including Reynolds number also, the derivation of Reynolds number, different flow regimes, then the flow in the pipe we discussed in very details. So here it is all the things are given, all the data is given, all the background is given, and also we have derived the equations, and then we have come up with the equation that is used for the pipe flow, and that is after derivation. And then we are driving the shear stress and the pressure gradient relationship, and also we are discussing about the why pressure gradient is constant in the pipe flow, and the velocity profile that we are describing here. Then we are going to find out the maximum velocity and the average velocity. Average velocity requires some strong mathematical background, that we have to use the volume flow rate and the V average, and then we have to integrate from 0 to R. So all derivation steps are given here, and all the videos are available. If you need the video course, recorded video course, you can avail that one, or you can also attend the live course that is going to be held from the May 2nd batch. And the velocity profile, the CF, everything is derived here, and all the formulas like Darcy friction factor is also derived in this course. This is the way we drive the CF, F. So F is derived over here. So this is the formula for the Darcy friction factor, and then also we have the relationship between the Darcy friction factor and the coefficient of friction, or the simple friction coefficient. And then we have the analytical data for all the variables for the given data. And so then we are going to compare. So these formulas all are derived in this course, and then we are going to compare our results with the CFD. Okay, meshing is discussed, the background data is discussed, meshing types are discussed, and meshing is discussed in a very detail. So all these important things are details are there in the course. And then we finally set up the problem and compare the different mesh types, different the mesh sizing, different meshing methods. So everything is given here in this course. Like this is a pressure drop from the CFD and the analytical data, and this is a velocity profile for different three meshes and comparison with the analytical values. This is the vector plots. And also this is not only limited to this part. We have the a second workshop is Anaka 0012. We will go through the 2D case and 3D case also. And also third workshop is about the heat transfer and the pressure drop in the shell and tube heat exchanger. Workshop 4 deals with the wind turbine, 2D Darrieus wind turbine CFD analysis. And this is going to be the transient case. And the workshop number 5 is the multi-phase flow, where we are going to study the tank emptying when the tank is full first initially, and then the tank is we have on the bottom with the orifice. When we open the orifice, the tank will start to empty from the bottom. So we have the analytical solution for the time it will require to empty a tank, and then we will find out the time from the CFD and compare them. So right now the course fees was $500. So we are putting at the around 85% off, only $65. Course will start from the May 6th, but if you register by the May 1st, you will get the course fees of only $65. Otherwise, the fees will be $150. Okay, not the $500, but $65 up to the 1st May, and then after that, before 6th May, the course fees will be $150 USD. So please hurry up, and you can contact me on this WhatsApp number. Thank you.